All right, so chapter 5, the beginning parts of it are not going to be like brand new to you. We've already kind of looked at some of this. It's more on probabilities. These are called discrete probabilities. Remember we talked about the difference between discrete and continuous variables way back in like chapter 1. We'll get a little review right here because otherwise no one's going to remember. So here we go, discrete probability distributions. They'll do an introduction and then binomial, Poisson, and hypergeometric distributions. The names sound scarier than what they really are. Also, the formulas look scarier than what they really are. That's the pattern we've noticed so far. Everything in statistics. Names and formulas are scary. When you actually do it, not horribly scary. All right. Especially if you're Brittany, who's like tearing this class up like it's the easiest thing she's ever done. If I were doing group work, I'd be in Brittany's group. What'd you do to your arm, Brittany? I thought you were an experienced rider. All right. I get bucked off a horse once. I'm never riding horses again. That's how it works for me. That's probably why I don't like horses. One time when I was a kid, I was trying to get a horse to stop, and my rein broke, and it just kept on walking, like toward a road, and like I'm trying to get to stop, and this horse must have been stupid. Like I would think a horse would be like, whoa, there's cars. Stop it. Nope. You didn't say whoa and pull back. Apparently I'm just going to keep on going. Didn't like it anymore after that. I don't like driving anything I can't control, anything that has a mind of its own. There you go. All right. So 5.1, Introduction to Discrete Probability Distributions. So discrete data, if you remember this, the values are whole numbers as opposed to continuous where the values can be any number. Okay? They're usually counted and not measured. So some examples they have that we might see in business, number of complaints per day. Right? If we wanted to have a complaint box out there, we could measure how many people complained or how many people gave positive reviews or whatever. The number of people, the number of TVs in a household, the number of rings before a phone is answered, and all sorts of other stuff like that. Continuous data, like I said, can take on any value, and it's usually measured rather than counted. So how thick is something? How much time does it take to do something? What's the temperature of something? Those are measured things. So this chapter deals with discrete data. We'll see that discrete distributions have these sharper data points as opposed to continuous, which are continuous. It's more smooth. All right. So discrete random variable is data that have outcomes that take on whole numbers. We just established that already. So you can read that. I won't read it to you since it pretty much just restates what we said on the last slide. All right. So discrete probability distribution. It's a listing of all the possible outcomes of an experiment along with the relative frequency of each outcome. And I said when we look at this, you'll see, oh, that we've already done this. We already did frequency distributions, and we've already done probabilities, at least the general sense. So this is just kind of combining the two things together. Okay. All right, so here's a discrete probability distribution. We do 2 coin tosses. We have 4 possible outcomes, right? We could have 2 tails, a tail and a head and a tail, or 2 heads. We put them on the chart. Number of heads, 0, 1, 2. The frequency, 1, 2, 1. Relative frequency. This is stuff we've done already. Here's the rules for discrete probability distributions. This is important. Each outcome in the distribution needs to be mutually exclusive of other outcomes in the distribution. Right? You can't have a head and a tail in the same flip. You can only have a head or a tail. So heads and tails are mutually exclusive. The probability of each outcome must be between 0 and 1. We've learned that that's the case with all probabilities, right? There's somewhere between 0, meaning it can't happen, and 1, meaning it will happen. And the sum of the probabilities of all the outcomes must be 1, meaning something's going to happen. The mean of a discrete probability distribution is the weighted average, which we've learned how to do, of the outcomes of the random variables that comprise it. There they give you the formula that looks scary, but we know it's not that scary. I'm skipping through that because we've done this. The easiest way, in my mind, for these is just to create a table, take the number times the probability, and that gives you the mean, or not, I'm sorry, the mean for that one, and then we add them all up. We've done it over and over, guys. The variance, same thing, it's measured as the spread of the individual values. There's the big scary formula. There's the shortcut. Well, when you put it like that, so easy. And then the standard deviation is the square root of the variance. Again, in my mind, the easiest way to work these out, we can't just use the standard deviation and the variance formulas in Excel because it's weighted, okay? So we have to measure, we have to multiply it out. So we just take the number, there's the mean, subtract it from the x1 minus, it doesn't look right, 0.25, that's 1. Oh, there's x1. I got confused. So we take 0 minus the mean, we square it, add them up, and that gives us the variance. Then we take the square root of the variance, and that gives us the standard deviation. We've done this already as well, okay? There's their shortcut method. Again, I think it's easier just to use the table. It takes a few seconds to set it up, and once you do, you're done. What this is valuable for, the mean and the standard deviation, is when we're trying to compare two different distributions, right? We want to know which distribution has more variability in it. Again, I think we've already learned this concept. They're just reviewing it for us because then they're going to move into additional types of distributions. So this is their example, is this call center in Atlanta versus a call center in Boston. Number of rings before the call is answered. You could see how if you were running this business, that you could do this and you could figure out who's doing their job better by measuring how many rings. That's not all of the job, but that's one job. Why does the phone ring so much more? So you can see in Atlanta, their average is 3.15. In Boston, their average is 1.9 rings. Their variance is 1.528. 0.69, standard deviation 1.236, and 0.831. So we would say Atlanta, not only does it take them longer to answer, they also have a wider variance and a wider standard deviation. So they're slower but they're actually, let's see. Yeah, they're slower in Atlanta and they're less consistent as well. So what we'd probably do as management is we'd go down there and try to figure out why that is, right? I think we're learning that in financial management, that a lot of times we can look at the data and say that tells me something, but you still have to connect it to what's happening in real life. Is it that they're understaffed? Is it that the way calls come in there, they have these high peak times where it's very hard for them to answer them as quickly, and that's going to create more standard deviation as well, less consistency? Or is there something else that we can do something about? So that's kind of an example of how we might actually use that information. All right, so the expected monetary value, all it is it's the mean of the probability distribution when we're dealing with numbers. So they have this, or dollars. So they have like this whole different term that makes you be like, oh wait, what's this? The expected monetary value. All it is that same mean that we calculate for all these other data sets, but when we're measuring it in dollars. In essence, think of it this way. The mean of a probability distribution is not what we're always going to get, right? Each time we do one of these probability distributions, we'll calculate the mean. That's the average. Another way of putting that is it's the expected value we would get if we did a large number of trials. We would expect that things would move toward the mean. Sometimes things will be higher than the mean. Sometimes things will be lower than the mean. But that's all a mean really is, right? When someone says, well, what's the average? What's the average cost of college? What does that mean when someone says that? It means it's about the amount you would expect to have to pay if you went to college. But you know, if you go to EAC, it'll be a little less, or if you go to Harvard, it's going to be a little more than the mean. But that's, so think about mean in that sense. Mean means the expected amount. So when we put it into dollars, it's the expected monetary value, or the amount that you would expect, or the average. In fact, average tuition, we would say the mean of a distribution of that would be the expected monetary value. That's all they mean by that term if you see it come up. So here they give you an example, calculation of the EMV, or expected monetary value for profit from crop yield. So all we do, remember, it's like the weighted average. We multiply 200,000 by 0.3, 300,000 by 0.5, 150,000 by 0.2. We add all those up, gives us 240,000. That's our mean, or our expected monetary value. All right, so the remaining 3 sections of the chapter, you can read it, I won't read it to you, but it's going to break down different types of discrete probability distributions. The first is called the binomial distribution. What would you guess about binomial distributions from their name? Yeah, there's only 2 numbers. There's only success or not success, right? And so it deals with all those things where there's only 2 options, like the flip of a coin. It can either be a heads or a tail. Or like, are customers satisfied or not satisfied? Or did people eat their whole plate of food or leave some plate on their food, or whatever? Okay, so that's how that's what binomial distributions, how they work. So the characteristics of a binomial experiment consist of a fixed number of trials, denoted by n. Each trial has only 2 possible outcomes. Usually they denote those as a success or a failure, even though we have to be careful with those terms because people like successes and don't like failures. But, you know, we could also say, you know, what's the probability that someone is killed in the first time that they touch a 220-volt electrical circuit? And we might define success as the person being killed and failure as them not being killed. So those terms sometimes get confusing. Nonetheless, either the event happened or didn't happen, and that's usually labeled as a success or a failure. The probability of success P and the probability of failure Q are constant throughout the experiment, and each trial is independent of the other trials in the experiment. That's important too. So the probability of P plus the probability of Q is always going to equal 1. So they're mutually exclusive, and they're exhaustive, meaning either one or the other has to happen. Okay, that's how binomial distributions work. So there's some examples. I like my electrocution one better, but hey, I didn't write the book. All right. So binomial probability distribution is used to calculate the probability of a specific number of successes for a certain number of trials. Given specified probability of success and a probability of failure. So we're given all of these things. So again, so here's the formula, and the formula can look a little intimidating, but really if you had to, and you had all of these variables given to you, you should be able to calculate this, right? I mean, so it's factorial of n divided by n minus x factorial times x factorial times p to the x times q to the n minus x. We could plug those numbers in and work that out. It's not crazy math. It's just a lot. And so, of course, we always look for shortcuts when we have a lot. So here's their example. 40% of all voters support Proposition A. If a random sample of 10 voters is polled, what is the probability that exactly 5 of them support the proposition? So the first thing I would do if I had to work this out by hand using the formula, I would say, okay, what's my n? N is 10. My p, or my success, is 0.4, which means my q would have to be 0.6, because p and q always add up to 1. All right? And my x gave me, was 5 of them. We want to find the 5 that support them. Remember, n is the number of trials, x is the number of successes, p is the probability of success, q is the probability of failure. So once I have all of those variables listed, I can just plug them in and crank it out. There it shows it. There's like a histogram. The mean of a binomial distribution is NP, where N is the number of trials and P is the probability of success. But it's kind of simplified because it's binomial. Because remember, we would find the mean in any of these types of distributions by multiplying it out to do a weighted average. Well, here there's only two choices, so it's just NP. Okay. Standard deviation is NPQ, square root of NPQ, or the trials times the probability of success times the probability of failure. Again, they give us an example where they work it all out. Awesome. Because as the number of trials and that goes up, this can get to be a lot of math. Some people use tables. You'll see these are in the back of the book if you ever want to use them. I don't think you will, but for each n, then they have a number of x's, which are the possible or the successful outcomes. And then the probability goes across, and you can just find it on the table. So that's available to people. But once you know that there is an Excel function called binom.dist, or binomial distribution, right? Nobody cares about tables anymore because we can just plug this in, and there's the formula. And of course, if you search it, it'll tell you that, right? But sometimes it's confusing as to what it means. This is also in your book if you forget it or you get confused. Tell you how to use this. Again, I hope at this point we recognize that what we're doing in this class is we're trying to focus on what these things mean and how we would use them more than we are about memorizing formulas. Because in a business scenario, like no one's going to ask you to like MacGyver the binomial distribution of something out in the field, right? Like you're going to have Excel available to you. And here's the other thing. I have never had to figure out the binomial distribution of anything in my career. But understanding the concept of it has helped me in decision making. I don't know if that makes sense. So I've never had to come up with like the answer, but I've had to understand how things are distributed and recognizing the difference between, is this a situation where we have just two options, success and failure, or is this a situation where there's a broader set of options? And understanding how probabilities work generally helps me a lot as a business owner. And so just remember that. Will there be some of you who go into an analytical side and end up having to use these sorts of things? Yeah, but if you do, you'll do it all the time. So you'll be very accustomed to doing it all the time, and it won't be hard at all. That's the thing with almost everything you learn between accounting and all the math classes is you'll end up grabbing parts of it that you'll use in a career, and you'll use those all the time, and the rest you'll be like, I have a frame of reference, but I understand the concept basically, and if I have to, I can Google it and figure it out, right? Remember, was it binomial.ds? What was it? Anyway, so that's how you do it in Excel. binom.dst, parenthesis, x, where x is the number of successes, n is the number of trials, p, the probability of success, and then you can choose cumulative equals false or cumulative equals true. And what that means is, if you say cumulative equals false, it means I want exactly the probability of x happening. And if I say cumulative equals true, then I'm saying I want x or fewer to happen. Because sometimes the question will say, what's the probability of having 2 successes? And other times it'll say, what's the probability of having, 2 or fewer successes, like 0, 1, or 2 successes. If it would ask me, what's the probability of having 3, 4, or 5? I would have to remember that they're all additive and they all add up to 1, so I could still do the true, do 0, 1, or 2, subtract it from 1, and that would tell me what 3, 4, or 5 was, or whatever, okay? And you'll see in some of the problems what I mean as you get there. Again, first day when we're explaining it, it's more like trying to explain a game to somebody. Sometimes you just have to play the game to figure it out, but hopefully that's valuable enough. All right, there they show you how to do it. All right, 5.3, Poisson Distribution. This is named probably like Poisson. I don't know how you say it. Some French dude came up with it. I don't know how you pronounce it. Anybody here speak French? Poisson. Does that mean fish? Les poissons. I think it does. A Poisson distribution is used for calculating the probability that a certain number of events will occur over a specific interval of time or space. So remember, the first one was for calculating the probability of something either being successful or not successful, or having a certain number of successes and a certain number of trials. This is different because now we're talking about the possibility or probability of something occurring over a certain specific time interval. So number of customers per hour, number of flaws per meter of cloth coming off a production line, that type of stuff. Okay? Has the following characteristics. These characteristics are important because, in essence, when you get a problem, you have to decide, am I using binomial distribution here, or is this a Poisson distribution? So that's why they give you these characteristics, okay, so to help you differentiate what type you should be dealing with. The experiment consists of counting the number of occurrences of an event over a period of time, area, distance, or the type of measurement. The mean of the distribution has to be the same for each equal interval of measurement. The number of occurrences during one interval has to be independent of the number of occurrences in any other interval, and the intervals defined in the Poisson process cannot overlap. So if we're saying for each meter of cloth, then that's easy, right? Because it's each meter. They don't overlap each other. We have to make sure when we're specifying a time interval that we don't overlap. So if you say between 11 and 12 and between 12 and 1, we created an overlap. You have to say between 11 and 11:59, between 12 and 12:59. Does that make sense? Here's the formula. Of course, they use Greek letters to make it even more confusing. But in essence, the probability of x equals the mean to the power of the number of occurrences times e, which is a constant, to the negative number of occurrences over x factorial. Piece of cake. Again, if you had to, could you? Sure. You could take all the numbers, put them in there, plug and chug, you'd be good. There's the variance. There's an interesting thing with Poisson distributions, and I tried to do a little research to find out why this is true, probably because I'm nerdy and was just curious as to why the variance would equal the mean. And I could not find something that was sufficiently simple for me to understand, but maybe it's because I'm a simpleton. The book just glosses over it and says, hey, a great thing about this is the variance equals the mean, and then doesn't say any more about why. You know, there's some interesting stuff out there, though. If you ever go and like YouTube it, there's all these weird people like giving you all these explanations as to why things are. Sometimes you just call it a gift and say, if I'm working with this, I know that my variance equals my mean and I can move on. I don't know. All right. Let me just be honest. I'm sure given a little more time I could give you a better answer than I don't know, but right now I can't. All right, so here's an example. They just plug it all in. Again, so what's the variable? It gives me the variables, 4, x equals 3. So, I mean, the math's pretty easy. Again, they give another example. Same thing, same math. Again, there's a table if you want to use it, but why would you do that when you can use that? I'm not a big fan of tables myself. It seems like the possibility of like screwing it up is high for me. Probably because I'm not coordinated. Can't bring my two fingers together in a straight line. But I can type in Poisson.dist, parenthesis, x, comma, the mean, comma, either cumulative, true, or false. And again, the cumulative true or false just has to do with, do I want the exact number for x, or do I want for x and all numbers lower than it? And again, that'll be clearer as you see some example problems. So they let us know that binomial probabilities can be calculated using the Poisson distribution when the following conditions are present. Why? I don't know, especially when it's just, you can do a function for either one in Excel, but you can. When the number of trials n is greater than or equal to 20, and when the probability of success p is less than or equal to 0.05, sorry. When those two conditions are met, you could use a Poisson distribution to approximate a binomial distribution. I don't know why you'd want to do that. I guess because it is a little bit simpler formula, and if you were doing it by hand, maybe is where people came up with that. But now that we have Excel doing it all for us, we'll just use Excel. But they want you to know that. I could see some homework problem that says, use the Poisson process to estimate this binomial. And you're like, okay, bro, if that's what you want. There's the formula. That's the Poisson formula. They give you an example where they do it just using that formula. Tells you that you can do it because it meets the conditions that it already specified. And there you go. All right. Yeah, I just, as I was reading through that, I was like, that's really great that I can use the Poisson process to approximate the binomial distribution process. But why would I do that when I could just calculate the binomial distribution process, especially, you know, I don't know. I thought it was interesting. I just don't see myself doing that ever. Okay. Welcome to math class, right? All right. Hypergeometric distribution is used when samples are taken from a finite population without being replaced. Samples are no longer independent in this case, right? So for the first two, we were talking about having independent relationships between everything. In a binomial, if I flip a coin, each flip of the coin is independent of the next flip. Just because I got a heads on the first one doesn't make it any different chance that I'll get a head on the second one. Okay? In the Poisson process, same thing. Each option is independent of one another. But in a hypergeometric distribution, what's happening is we are pulling a sample out and not replacing it, meaning it's going to change the likelihood or the probability of the next occurrence happening. Okay? So they're no longer independent. When sampling is without replacement, the probability of success changes. That's what I just said. So we have to use the hypergeometric distribution. And because hypergeometric sounds freaking awesome. Like if you bust that out while you're talking to your parents, like it looks like the relationship between these variables is no longer independent. So we're going to have to approximate the mean and the standard deviation using a hypergeometric distribution. Your parents will be like, man, that money we're paying for college, so worth it. Actually, I realize most of you are probably paying for your own college, but hey, you still want to impress your parents? Pull out some statistics speak on them. Okay? Here's the formula for the hypergeometric distribution. Again, you're like, okay. No, you Gusta. All right. Again, we could do it if we had to. We don't want to do it. But in essence, we're going to have to do an n minus r and an n minus x, right? So we're going to have to do this for each one of these. We could crank out the numbers if we had to. This one's a little harder. Again, we don't need to because we have Excel and we love it. So they do give us an example. 5 of 50 accounts are delinquent. If the auditor randomly selects 10 accounts without replacement, what is the probability that at least one is found to be delinquent? We need to find the p, the x is greater than or equal to 1, equals 1 minus p x over 0. We have all the information there. We can plug it all in. It's doable, but not pleasant. Okay? And if you want, I mean, seriously, if you want, we could take a day and I will show you how to work each one of these by hand. It's not my favorite thing, and it's not something that I do all the time so that I'm terribly proficient at, but it's a matter of plug and chug math, right? Figure out your variables, plug them in, do the math, and you can come out with the answer. The mean, standard deviation, again, we could plug them in, work it out, or we can use hypgeom.dist, calculates the hypergeometric probabilities. Again, n is the population size, big N size. R is the number of successes. N is the sample size, X is the number of successes in the sample, and then the cumulative true or false. And that's it. All right. If I can express anything to you, it's that as you look at this, you're going to figure out that a lot of it is stuff we've already done. It's already been introduced in the previous chapters. And then the rest of it is stuff that we can use Excel pretty effectively to do. I'm nearly begging you to read through the chapter if you're not doing that. And I know it's hard in the electronic version, but he really explains some things that helped me understand it more deeply, but it's hard for me to express in the way that he does because the guy who writes the textbook's an expert in this stuff. I don't claim to be an expert in this stuff, but I understand it well enough that I think I can explain it to you. Anybody have any questions about this? Again, it's the kind of thing that once you do it, once you get into it, I think it'll be easier actually than the last chapter was.